Peter Hill here, and hello to Professors Lisa, Dave, John and Simon. I'm going to give a little talk about this diagram I have up here showing the 5 scales of the universe, and going to actually talk a little bit about, for this top one here, the need to study some group theory. I'll give an overview for it. So what's overall happening is that I've obviously doing a bit of cognitive rehab, lots and lots of podcasts, slowly improving in video presentations like this, I hope, as I'm going through, trying to get the sort of the brain working, and so studying areas. And of course, if I don't have an organisation, I've got sort of no limit. I have to actually really understand things, and I think, understood things on certain levels. On terms of quantum physics, I've really understood wave functions and molecules and stuff like that. Group theory is something I really have to get used to. I'll get back into that in a short while. But in general, what I've discovered is that you need different types of maths and different types of physics for different scales. And teachers have come in with essentially the model they have in the cupboard is human scale, and then they get students really confused as you go through different scales going through here. And you need different types of maths, but I've found here for the group theory up the top here that this is something that you really have to get into. So let's have a little bit of a talk about the different scales. There's 5 scales, a trillion to 1, that is I get something and I blow it up by a factor of a trillion. 1 to 1, the scale that you're watching me at the moment. 1 to a trillion scale is a very useful scale for talking about the solar system local star group, and you'll see pictures of the Sun and Alpha Hydrae. A trillion is 10 to the 12, a yotta is 10 to the 24, a yotta meter, and that gives you the galaxy and stuff like that. And then you can't go a trillion, it's actually a million trillion, gives you the size of the universe, that little red dot there. And there's different physics things, so there's no outside the universe, for instance, so there's lots of things to go. Now what I'm going to do is just do a quick view into group theory, just to remind you. My initial brush with the group theory was studying quantum physics, and there's basically SU2 and SU6 are the big things in physics. SU2 for spin, handling spin and antimatter, or I suppose SU2, spin particularly, of quantum functions. Then there's the orthogonal nature, the complex nature of quantum wave functions. They really apply to group theory rules about matrices, etc. Then SU6 does the entire standard model. It looks inside protons and stuff like that. So you really need to understand group theory. Initially it was sort of a convenient notebook way of storing information and remembering rules, but then there were rules that helped you make the correct predictions. But when you saw things, so particularly the thing that really struck me off is that a Fridge Magic has got twice the magnetic field it should have, and things like that. And what is a fundamental particle as we get down to the scale. So just let's do a quick review of the things off the top of my head. Bear in mind that I'm studying this and it will take months to slowly get through it. A group is a bag full of numbers, and it has 4 properties. It's got the identity element, so it's got a bag of elements, and so one of those elements is the identity element. So this element will not change if you operate it with another element. Close it with another element, it will not change that element, and that's putting 2 elements together to get a third. It's called closure. We have the idea of association. If I've got 4 in association, I'm going to sneeze here, I'm sure. If I put 2 together, or 2 together, it won't change the result, but I can't swap around. I haven't done a very good example of that. So that's association, and then inverse. And there's a whole series. An inverse is two elements together will give you an identity element. And there's a few unusual things where things are its own inverse. So with the reflection, I can reflect it twice and get back to where it was, or I can rotate it 180 degrees twice and I'll get back to where it was. So there's a whole lot of interesting aspects to it. There's other aspects, like group theory is very much what's left, what people see when they see a whole series of different fields of mathematics. What is the same aspect of it? And it sort of allows you to go across. And this is what I really want to see here, because we've got the group theory of the algebra, and we've got the group theory of the rotation of the universe. So I really want to get down to it, because we're going to talk about these little molecules, these things up here, which are the nuclei, the proton and alpha particle that's up here at the moment. So let's break off from group theory. I haven't done a big discussion of it. I do want to stop before I go too far, is to say that SU and SO for people, for us physicists and chemists, special just simply means that the special means a class subgroup of elements that has a determinant of the matrix of equal to 1. Unitary is a series of restraints on it. It's quite interesting. But a unitary is standard quantum mechanical. It's that the inverse of an element is the complex conjugate of it. That is the things that are multiplied by, I suppose, minus I, right through. I'm just really trying to think about that complex conjugate. A orthogonal one is the inverse is the transpose of the matrix. So that would be, say, like standard physical rotation. So that's the interesting of it. The S and the U, and you've got general linear. A general linear matrix is a matrix which has an inverse. So you've got these sort of onion shells of different things. Now, just before I get into this, one of the things which I've been speaking with Professor Dave is the scale laws in science. But there's a sort of very interesting side bit before we really get into it, is that the scale laws came from analysis of Dante's 9 circles of hell, and this was a great intellectual magnet of the age. For this is not necessarily the most religious people. This is the common people got really interested in this, because you had the individual could go through these known circles. So you've got different circles, and there's a sense that you're on a journey going through. And so this scale system here. You can go in the scale of very small to the very large, and you can imagine going through a journey. And as you sort of expect to go through a journey, you expect new rules for each level, and this is very much here. Now, the first level is 1 to a trillion. Sorry, a trillion to 1. Did I say that? I won't bother editing that out. A trillion to 1. So a trillion is a million. A millionth of a meter is a micron. Micron is the Greek for small. The Greek for dwarf is nano. So a billionth. A pico is from the Spanish for just a little shaving. So let's go. So it's saying that a meter is a picometer, and so therefore a kilometer is a nanometer. And so so give you a sort of an idea. A kilometer is a nanometer, a picometer, and a hydrogen atom is 52 picometer radius. It's a Bohr radius. So basically an atom the size of a 2020 one-day cricket field, slightly reduced field. This is the size of an atom. Now, we just sort of pause at this stage. Quantum physics doesn't have those little classical electrons. It has the electron as a large, spongy ball which can actually support weight. do all the things the atom does, the atoms do. Quantum physics does, classical physics does none of it. There's no empty space in quantum physics. So the electron is a fairy floss which goes from way beyond a meter. 100 meters is where they've got 50% of the atom in 104 meters sphere. And it's sort of going in, and it's all electron all the way through, getting up maximum in the very center. In the very center, you have the proton. The proton is a femtometer. Femto is from the Danish or Norwegian, could be either. From that era it came from. I suppose Denmark and Norway was the same place. But that's a 15th, 10 to the minus 15. And so that, if you go right into that, 10 to the minus 15, that's 1 millimeter. And you'll see up here, I have a proton which is 1 millimeter across. I'm going to have a start to look at here. It looks as though it has a surface, but it doesn't have a surface. Quantum mechanical things do not have surfaces. They don't have an inside or out. They only grade into existence and out of existence. It's got a very defined space because it's held in by the strong force. One of the things I want to point out to you is that you see if you add a proton, sorry, a neutron to make a deuterium, that little D one there, it is easily 4 times the size. So 4 times the volume, yet you've only doubled the volume. And of course, this is the problem with the liquid drop model of Bohr from 1936, which lasted 1 month officially before it was chucked out of science to be loved forevermore by schools and taught to thousands of school students. A sort of a thought bubble from Bohr. This is so amazing that it's got through. But indeed, the neutron is not a separate hard ball with some sort of force on it. The proton can't get into it. That's completely incorrect. The neutron actually exists through the proton. And the modification, what you're seeing, the size, is the modification of the strong force coming out. And you'll see the tritium, you add another neutron, it actually gets smaller still. And then your alpha particle is your smallest one out there. That's got 2 protons and 2 neutrons. The important aspect, I just want to go on that for a small point, is that these are featureless things. These are essentially they're made up of fundamental particles. And being a fundamental particle, they can't rotate. So if I fire something at a proton or an alpha particle, something like that, it's not going to have a distribution of spinning out one way more than the other. It's not going to have, your spin's not going to be show up in its scattering due to the actual angular momentum rotation. It's got the property of angular momentum but not rotation. If we just go down for the electron is a fundamental particle. Fundamental is by saying that there is nothing smaller in it. And if there is nothing smaller, there is no machinery in it. There is no valid model that I can bring out of the cupboard because it's completely wrong. From the moment it has a part, it's wrong. And really, the way we really should say is model, it should be, fundamental, we should say it's magic. That is, that it doesn't have a way that you can imagine. You can comprehend it through the maths, but you cannot imagine it. So an electron has a spinning current in it, and it's got an angular momentum, but it's only got the property of a magnetic moment, and it's only got the property of angular momentum, but it is physically not spinning in our universe, and it is actually truly of SU2 symmetry, in as much that it has 720 degrees rotational symmetry, but it cannot be physically rotated. It's not physically rotating, but the entire universe is rotationally invariant, if that makes sense. So you've got the angular momentum of photons going back and forth between it. Sorry about this. We'll just so this is where group theory really gives you the explanation that we're really hunting for. So given that we are fighting against dumb teacher who brings out a model and says, here is a physical model of a proton, here it is, and I want you to believe and understand it. It's sort of teaching a whole lot of wrong things. That is not, you can't give a model of something which is fundamental, which doesn't have parts. You can't put a as I've said, you can't put a mark on an electron or a proton and get it to spin because it doesn't have those features of it. Just to get back into the inners of a proton is not fundamental. So a proton has an excited state, which is the delta particle. This goes from spin, isospin a half to isospin 3 on 2, going up above it. And the nucleuses have excited states, and they have linearly excited states or line states, which are quantum mechanical. That is, that the different neutrons and protons of excited states have symmetries and spatial nodal lines, but they have nodal lines that don't have components. It's not I can't rip off a bit of a wave function. It's all the same things. There's sort of questions I do have about time, because we do separate time separately in the Schrödinger wave equation. I just want to quickly say an atom which is spinning does not have its physical electrons. Doesn't have its physical electrons moving around. Moreover, it's the complex phase of the stationary wave function is moving around. That's what's moving, and if you apply the momentum operator to it, you apply it to the time dependent. So spatially, it is still, it's got a time dependent phase spinning around, so it looks similar. So the model of an electron spinning is so wrong, because the electron is actually spatially stationary. There is no, what we understand as momentum, that is unit of mass, unit of volume moving from one point to the other. Our definition of motion is not correct coming out here. I do want to say something. So those particles up there are fundamental particles. They are really small, and you get an access to it, and a lot of the modelling which we use is incorrect. I just want to quickly say about the internals of the proton. It's got 3 quarks, 2 up and 1 down. It's okay. The quarks are a tiny fraction of the mass. In between it are these, again from group theory, gluons, and there are 8 possible gluons. So gluons are oscillations in the strong force field. So you can actually, there is a theoretical idea that you can make a glue ball, no quarks, you can just have a stable blob of excited state. The gluons actually attract each other, and so build up mass. So your gluons, when you fire something into a proton, it will scatter, but as it scatters, the gluons will stick to each other and form a jet. And this is one of the things that the sort of telltale signs of what's inside a proton, and for the force of it. Again, the shape, spatial, it looks as though it's got a surface, but it doesn't. It's got the wave function finishes very quickly due to the strong potential. So you have to go into it. So there's the area on force, on group theory, and people who are just watching for the group theory thing, you might want to switch off now. We go up to the other levels. I want to quickly go over those. You've got the ball bearing, the person holding the ball bearing down like this, and that's the 1-to-1 scale, and this is where school physics is great. You should just leave it as it is. The next level up is the 1 to a trillion. This is the scale model I mentioned to Professor Dave, and you have Alpha Hydrae there, which is to scale, the size of Alpha Hydrae, and that's on to scale distance. There's one in Glenbrook, Solers in Glenbrook, and the other one's in Professor Dave's office. So I want to eventually get it there, and this is all trying to say, what do I give to Professor Dave? So I'm just trying to work out exactly what to give. This again's got different physics, different ideas. I want plasma physics to go in with the internals of the sun. Again, very, very poorly taught. The next level up, 1 to a trillion, seems an obvious thing. And that scale, the size of the galaxies, is the sun is a trillionth the size of the galaxy. You can see it there. And then Andromeda, the distance from Andromeda to Milky Way, which you see here, I'm pointing to it in general, is to scale, drawn to scale to be the actual distance. It's about 2.5 centimetres on scale coming towards us. Then we get up to the scale, so that's a yotometer. Yoto comes from the Greek for 8, a yotometer. And so it's a big YM rather than kilometres. Okay, and the universe itself is 880 yotometers across side to side, and so 880 meters, a millimeter is a millionth of a kilometer, so 0.8 millimeters width is the universe. The only thing I want to say about this little universe is that again you have to use a different type of maths. It's not that it doesn't have a surface. We can only be inside a universe. There's no outside of the universe. So the universe is the very first point in time. And everyone is always stuck in the very centre of the universe, where they're now, and they're equidistant from the very first instant of time. Everyone is equidistant. It's one of those amazing things. So if you look back, you're looking back at the universe. So this is again one of the things that where clumsy teachers use models just out the door, and the student learns a lot of things, can learn to answer a lot of questions, but learns a lot of misconceptions along the way. So similarly true, there's a moral to this, that you can learn a misconception about the universe without seeing it to that size. It gives you the impression that you're going to be outside the universe and that there is a bigger universe. Getting back to it, just in summary, the real push I'm trying to do at the moment is this long, hard slog of working up a framework for teaching. So I'm doing a whole lot of things like that. This is building quantum oscillators and electronics, and organising teaching structures. But underneath that, I have to really understand group theory and see if I can pull apart the real reason as to the real physical explanation besides a naming convention to explain why fridge magnet is twice as strong as it should be. Thanks a lot for watching.